All right. So we're going to pick up from last time. We're looking into the synchronization layer for multiplayer real-time video games, or I guess more generally, multi-agent environments with real-time video, real-time environment generation. So there needs to be a synchronization layer built for that. It exists for traditional rendering engines, but it doesn't yet exist for rendering engines that are built on a world model. So, and it seems like that's going to be big in the future, given, oh, I should share my screen. Given papers like this one, talked about this in the previous videos. So, I'm trying to understand how the synchronization layer works for traditional rendering engines with Claude. And so far, what we've learned is there's this library called Photon Quantum, which implements client-side prediction. I actually don't know exactly what this is doing. I tried understanding it last night. I think I might just have to read the code to really know, but this was its explanation. It's not really client-side prediction, so that's not exactly correct. What it's saying. It somehow ensures, yeah, it's doing this thing called deterministic lockstep. Oh, there is client-side prediction, but yeah, it's doing something else called deterministic lockstep. Anyway, the point is, it's some library that people who are building games using Unity or Unreal, which are game engines, it can use Photon Quantum's code to build a synchronization layer for multiplayer games. And it'll handle all the client-side prediction, rollback when the client state disagrees with the server. This company is a $500 million company. So, and it was built over 20 years. So that's not ideal, but if I'm taking Photon Quantum as an example of what I would do. But it shows, there is value in creating this synchronization layer. And there's many implementations of that layer. There's Photon Quantum. There is SnapNet Coherence Norm Core. Yeah. So those exist. And then there's network quality of service plays, which is like, instead of building this synchronization layer, why don't we just make the internet faster so that you decrease the need for a synchronization layer? So Subspace was a company that built a faster network infrastructure, which multiplayer gaming studios could use for a faster connection between players in the same game. But apparently this didn't work because the infrastructure costs were too much to maintain, and they died. I was reading about this company last night. They had like 150, 200 employees. They were serious, and they had very good, like a quality team. And then at some point in 2022, they cut half their team because their costs were running too high. But they hit eight-figure revenue in 2022. But yeah, their costs were too high. They cut half their team, and then the other half lost belief, and then they just died. So there's Network Next. This guy, Glenn Fiedler. Yeah, Glenn Fiedler. He's some guy that wants to build a 100,000 player multiplayer game, a space video game. He blogged about it, and he built this company called Network Next, which it optimizes the route that packets take to get from client to server. And he has some post online where he shows that the round trip time can decrease from low hundreds of milliseconds to sub 100 milliseconds using his infrastructure. So that's another approach. Make the internet faster instead of building the synchronization layer. And also, I don't think this is correct. Network Next still exists, so it's both died as false. 3, latency streaming tech. Parsec, I don't actually understand what this company does fully. But what it says on the website is, like, suppose you have a laptop that's not that powerful. They have a bunch of cloud instances of servers that are powerful, and then your laptop communicates with their high performance computers. The game runs on their high performance computers, and there's just a stream of pixels between their computers and your computer. So all your computer needs to do is display pixels. Their computer runs all the game logic. Their computer acts as the client, and then separately there's the server which hosts the actual game. And their value proposition is, well, we created this highly optimized networking stack. This highly optimized networking stack. Let me show you. To stream those pixels efficiently. Let's see. Yeah, this thing. That's peer-to-peer. I mean, I don't know. Yeah, so this right here is their value proposition. They have some optimizations for the networking between their computers and their customers' computers. So I don't fully understand why does that, eliminate the need for a synchronization layer. I guess their point is that if you use their network, then you'll have a fast connection to the game server. And so if everyone is using their stuff, you don't need any synchronization layer. But you can't guarantee that everyone uses their stuff for a game. So I don't see how that eliminates the need for a synchronization layer. But anyway, Polystream, haven't looked into this that much. Orchestration backends, multiplay to Unity. Yeah, so this thing, Multiplay is this company that offers bare metal instances. I was looking into what that means. So when let's suppose I'm trying to serve a game. I've coded up a game and I want people to play with it. Okay, so I'm running the game on a server. Maybe I get an AWS instance. When I get the AWS instance, I don't have granular control of the processor that I'm running on. AWS exposes what's called virtual CPUs to users, which, like, there's a layer that sits, it's an abstraction on top of a CPU. There's a layer that sits in between the hardware and what I see as the hardware, as the user of their AWS instance. And so I don't have granular control over the processor. Whereas if I rent an entire bare metal server, which is something that Multiplay offers, then I can modify the server however I want. So that's useful for people who want to host games, because I guess there's like tough requirements, stringent requirements on the efficiency of the host. So these companies got big, but apparently AWS is trying to take that business back now, and they're offering. Oh wait, before I go to that, Multiplay, they offered a full orchestration layer. So they offer these bare metal instances, and they offer an orchestration layer on top of those, which says, run your game on this bare metal instance, and if the traffic overwhelms that instance, we'll fall back to cloud. And they handle all that logic for you. But apparently part of the reason people use Multiplay is because there's huge bandwidth requirements for multiplayer games. Egress bandwidth, meaning like from the server to the clients. And that is costly if done in a cloud. So that's why people use bare metal instances in addition to the ability to control the hardware at a granular level. But AWS recently made egress bandwidth free. I think this was like literally a month ago. So people are saying like, oh my God, this is crazy. Now there's going to be all these multiplayer games that were previously not possible to create because they're cost prohibitive now are going to be possible. So we're going to see a huge proliferation of multiplayer games from smaller game studios that couldn't previously afford it. Now, so that's like the kind of the ecosystem of multiplayer games in the traditional regime of hard-coded rendering engines. And then I asked Claude, like, okay, extrapolate that ecosystem to what needs to exist for world model generated games, multiplayer games. First it's saying that there is no synchronization for multiplayer world model multiplayer games. The only synchronization is sync by centralization, which isn't synchronization at all. It's just saying, that it shouldn't say sync by centralization. That's not syncing anything. Apparently there is apparently there are some attempts to fix the synchronization problem, and this Enigma Labs and Solaris. So I need to read about those, but from what it's describing, I don't think it's really solving the problem. Yeah, and it acknowledges that the sync problem hasn't been solved. So Claude's kind of being unclear here, I think. But here it's just saying, like, look, all these world model AI multiplayer games are raising so much money. Everyone's excited about it. Once any of these labs offers API access for world model generation, we're going to see a huge proliferation of multiplayer AI generated video games. And then everyone's going to have this problem of synchronization. Okay, so now let's extrapolate the plays. Yeah, it's saying photon quantum's approach is what transfers the best. So let's just skip here. This is where I left off. I'm trying to understand. I'm trying to understand this. Claude is very confident that this is a good idea, but I don't fully understand this actually. So this is what I'm digging into. Let me read this again with a fresh mind. This I've looked into. So H.264 is a codec for video, and I think it's open source. H.264, is this open source? Oh, okay. Wait, so who owns this? Who owns the license? Oh, wait, so who created this thing? I think all the big tech companies got together and created this together. No? No. Okay. Okay, but I just want to know, like, does someone make money from this? What? Wow. Okay. So I was completely wrong in my impression. So I thought that these audio video codecs mostly don't make money. Most of them are open source. I know for audio there's something called Opus, which is definitely open source, and that's like the standard. I mean, there's one other popular one, which I don't know whether it's open source. So okay, so that means that this is actually a viable idea, but just to explain this, if we're in this world model AI generated multiplayer game world, and the thing that's being communicated between the server and the client are latents as opposed to pixels, then there needs to be a codec that's optimized for transporting those latents. Not the for the transport layer, you would just use UDP or whatever, something standard. I don't know if there's room for optimization there, but for encoding and decoding, I would assume that the optimal thing to do is different for encoding and decoding latents than encoding and decoding video or audio. And I don't think a codec exists for latents. But like, I don't even know if that makes sense though, because like, what is a latent, right? A latent is just a tensor, and it doesn't really have any known exploitable structure in the way that audio and video does. So yeah, I'm less sure about this one. Also, you would need to somehow get everyone to agree on your standard, to use your standard, and you would have to hope that enough software starts using your standard so that your standard gets baked into the hardware. And that's just it's very difficult to get network effects like that. And also, I don't believe that latent. First of all, like I don't even know if people are going to transport latents instead of pixels. That's a question that has to be answered or thought about. And even if they do, I don't believe that the structure of latents, there's some inherent structure of them in the way that audio and video does. Like maybe some research is done, 2-3 years down the line that completely changes the structure of the latents, and then maybe that invalidates the codec that I would write. So, I mean, I guess this is saying that I'm wrong. Let's see. What does this wave one do? Okay, so I guess this is a counterexample to what I'm talking about. Let's see. Let's read about this. Sec. Okay, that's pretty interesting. So that basically is a pretty strong counterexample to what I was just saying. Now, just want to know, like, what do they do differently? Just tell me. Okay. This is better than I thought. Get more coffee. Okay. This is interesting. But Okay. I see. Okay, so this is saying if the latent is discrete, then you can, and the distribution is known, then you can compress it very efficiently. Okay. But what is the hyper prior here? Hyper prior is the prior on the distribution of the discrete latent. Where does this paper say hyper prior? Effectively capture spatial dependencies in the latent representation. This. Okay, wait. Okay, let me get through the entire intro. All right. Let's just open a new chat. Okay. Okay, so you have X. You quantize X. So X is the coordinates are continuous. You transform it into something where the coordinates are discrete, so you quantize it. Rather than alternative, yeah, then, okay, quantization, okay. Entropy coding methods. I don't know what these are, but I can take I probably can take a guess at what it is. Entropy coding relies on a prior probability model of a quantized representation, which is known to both encoder and decoder. Okay. Yes. Okay. The entropy model used to compress the latent. Okay. Distribution. Okay. Need to distinguish between marginal distribution and entropy model. Method which is used to infer alternative representation. Why? Average code. Decoder pair can achieve. Okay, wait. So what is M? M is the marginal distribution of the latent representation. Okay. Okay, y hat. Wait. Y hat is the quantized latent. Okay. Okay. Oh, okay. The expectation of the quantized latent, the expectation over the distribution of the quantized latent of this quantity. Sorry, that's what this means. And this is some measure of entropy, which I'm just going to skip that. But the point is, this is a theoretically, this is a lower bound on the average code length. Yeah, the smallest code length. Okay. Note that this entropy is minimized if the model distribution is identical to the marginal. What is the model distribution? Fully factorized entropy model. Let me just ask it to explain this whole paragraph. I'm pretty sure I get all of this. Let me just read the rest first. Let me have it start thinking about that. Transmitting side information. So you have parameters. You have your quantized latent. You have your actual image, the final rendered image. X tilde. Wait, where's X? It didn't define X tilde, but actually, wait, Y hat. All right. Okay, I actually don't know what this means. I think I'm not supposed to be able to know what that means until later on. So skip that. Okay. I mean, I kind of get what they're saying. In addition to the encoder and decoder needing to know the distribution of quantized latents in order to decode the entropy compressed, what was it called? The entropy coded quantized latents. They also would benefit from some extra side information, from receiving some extra side information alongside the compressed quantized latent in exchange for being able to make the compression ratio larger. That's what it's saying. Okay. Okay. Mm-hmm. Yes. Okay. The rate. Wait, what's P? What's P again? P is entropy model. Okay. Wait. The rate is a. What is an arithmetic coder? Yeah, compression is. There's a lot of stuff expression. Okay. I see. And you just recursively do that? Okay. I see. Okay. So now back to this. Okay, sure. So you need to know these frequencies. That's what the probability table being referred to is. Okay, now the rate is a cross entropy, and the cross entropy decomposes. An arithmetic coder driven by model P spends blah bits on symbol blah, but actually arrives at the coder is drawn from M. Yes, okay, so the expected rate is equation 1. What's equation 1? Expected rate is equation 1. Okay, sure. But by the way, why does it spend that many bits? First of all, y hat is a vector. P of y hat is the frequency. Oh, I see. This is saying, this is saying if y hat happens to be a high probability quantized latent, then it takes fewer bits to represent it. Yeah, and that makes, if you're using an arithmetic coder. Okay, so that's fine. So the expected rate is equation 1, okay? This thing decomposes as this thing. H of M is the Shannon entropy of the true marginal. I don't know what the Shannon entropy is. And the KL divergence satisfies this. Sure. The model distribution, i.e. this P sub y hat. In other words, our frequency table is identical to the true frequency table. Okay, sure. Yes. Okay. This is exactly what I said. Why fully factorized then guarantees waste? Fully factorized, I think it just means like not accounting for any covariance. Yes. Right. Sure. Yeah, I don't care. Figure 2. Okay, so now let's go back to this. Okay, so this is saying instead of spending more bits trying to match this guy to this guy, the model distribution to the true marginal. And okay, so why would you need to spend more bits in order to do that? You would have to spend more bits in order to do that because if you don't use a fully factorized entropy model in your frequency table, has to include other stuff. Like, let me show you this. Like you have this frequency table. Yeah, you have this. It's just fully factorized. Okay. It's fully factorized because in each row you're only considering each character alone. Although, wait, okay, bad example. Wait, like you have this vector space, and then you have a frequency table for each coordinate of the vector. As opposed to having a frequency table for like tuples of coordinates. It's a good example here. Like, suppose you had a vector space, a three-dimensional vector space where the first dimension is red, second dimension is green, third dimension is blue, RGB. And then you see that in this vector space, the red dimension is always either 0 or at maximum value, 255. And you see that green is always at 0, and you see that blue is also always at either 0 or 255. And if you fully factorize this thing, you're going to have a frequency table which shows, 50-50 for red, 50-50 for blue, and 100% for green. And that's it. But that frequency table doesn't contain the information of how red correlates to blue. And that's information loss. And in order to have that, you would have to have another row in your frequency table. So you have to spend more bits if your entropy model isn't fully factorized. And you don't want to do that because, well, I guess like you only need to communicate the entropy the frequency table once, right? Let's see. Okay, I don't. Wait, where did I get into this? God damn, bro. It's crazy. Wait, what's first? Silicon, okay. This is the thing that worries me, right? Because just to explain this, I was asking Claude why this company Parsec has built this networking stack for efficient pixel transport between client and server. And I was asking it, well, why can't that networking stack be reused for transporting latent representations of the video instead of the video itself? And why wouldn't that be pretty close to optimal out of the box, considering that both video and latents are just tensors in a network? Yeah, tensors. Okay, in hindsight, that's a stupid question, but the answer is that the structure of the tensor that represents pixels is different than the structure of the tensor that represents the latent, because the pixels have things like spatial pixels that are close to each other are usually have a similar value. The same is not true for the latent necessarily. Also, the loss that we're willing to accept for for pixels is different than the loss we're willing to accept for the latent, because the loss we're willing to accept for pixels is based on human perception of those pixels. Like if we quantize the pixels in a way that doesn't affect perception of those pixels, then we're okay with that. Whereas with the latent, it needs to be decoded on the client side. So like if I perturb the value of the latent by some small amount, then it might, after being decoded, it might change the pixels that get displayed at the end in a significant way. So those semantics are different. That's what it means by loss semantics. This one, fourth, the temporal dimension, and all, yeah. So that, regarding that loss semantics, that compression has to be learned. Yeah. Like there's no hard-coded rule that's going to apply to all possible latents, right? Because it depends on the weights in the thing that decodes the latent to the pixels. Um, so like the decoder needs to, and the thing that's compressing the latent needs to be jointly learned. An efficient latent stream wants p frame equivalents, predict the next latent from history, transmit the residual, which is a small learned model, i.e. codec and world models start blurring together. So parsec class transport, yes, reuse wholesale code. Anyway, okay. Let's go back. Let's go back to this one. What's p sub x? Oh yeah. All right. Okay. So this is saying you have your input image, you have parameters of a network, you apply this network G sub A to this image with these parameters, and out of this you get a latent. Then you quantize that latent, and then you say what's the probability of that quantized latent under my entropy model, and then uh, what is the implied number of bits that's required to represent that quantized latent under my entropy model, and then take the expectation of that. So this is the expected number of bits. This thing is high, the code length is high, if it's low, then slow. Okay, so why quantize it all? Entropy coding, yes. Okay, blah, blah, blah. The destroyed information. Wait, theta sub g. Okay, so rate is the how, yeah, and distortion is expected, yeah. Okay, we're trying to minimize the sum. Gradients with respect to this thing are zero almost everywhere. Okay, sure. How does how does that help? Okay, I get it now. Okay, sure. You can do that. Now, what are you calling a hyperprior? Wait. Okay, the takeaway here is that there are fancy ways to compress video. Okay. Okay, wait. Partition the system into the shared core, the minimal state all players must agree on, positions, blah, 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 involved by a small, is a pure function. State, all inputs, seed, next state, bit identical, okay. Counter-based PRNG. What is this? Counter-based random number generator. Okay. Quantum's RNG in-state trick at the neural level. Okay, the big, expensive, freely sampling diffusion models that turn shared state pixels. Okay, so this is saying the server client communicate a very small amount of information compressed. And the world is rendered at the client by the client. Big, expensive, freely sampling diffusion models. In particular, what is the flow for a multiplayer game? What is the flow of data amongst host client for a multiplayer game? I want you to represent the host as some shape. Tell me what the host owns pictorially on an HTML page. And draw arrows to indicating what data gets sent from who to where. So maybe I think idea A is saying that the latents get transported from the host to all the clients. And then there should be separate shapes for all the clients and what the clients do with those latents, what they're sending back to the hosts, and the timeline of everything, like what's delayed and what isn't. And ideally, if you can animate it, that would be great. So I can visualize everything. And the picture should demonstrate to me what the actual product I'm building is versus what I'm not building, what's owned by the frontier labs themselves or the world model builders themselves. Anyway, coming back to this one. Let me think about this while it's giving me an answer. Like, okay, so you have these world models. Let me just ask Google, actually. Hello?
My car got towed.
What? Oh my god.
Car's on the fucking street cleaning today. So I have to get my car.
Okay.
Go straight there. Okay. Well, my Uber's already here.
Uh,
But we're gonna Uber home, so I guess I'll come home and then.
we'll figure it out. Yeah, come home, we'll figure it out.
Okay.
All right. Love you. Bye. My girlfriend's car just got towed. Um, Okay, let's try to understand this thing. To understand the architecture of this, we need to understand this. Okay, simple enough. Okay. Why does there need to be an upsampler? The upsampler, like, why not just have this thing upsample? Presumably, it's because this thing isn't fast enough, right? Okay. I don't think this makes sense though, because like this referee kernel is a function this referee kernel so you're given a state of the world, and this, has positions, velocities, score, whatever. Then you have people's inputs. And then you have a seed. And then you have this. And based on to know how this is planned. I mean, this is not at all how I thought it would work. So Mira, the paper is simulating on this. Okay. Why don't we take some notes here? So first of all, I want to do some research on anything that has been said by the World Model AI Multiplayer Gaming Labs, XAI, general intuition, etc., about the architecture for serving these worlds. Look at the key, identify the key researchers, employees, public figures associated / that work at these companies, and any social media posts or podcasts that they may have done in which. What's up? Give me a sec.
What?
Give me 1 sec.